to be okay. Okay, now we are in chapter 2b. We will start discussing about the application of bridge, okay, in estimating uh, in electrical measurement. Is in either estimating resistance, capacitance, inductance, and etc. Okay. So now we look at the resistance measurement technique using what is called as Wheatstone bridge. Okay. So Wheatstone bridge, okay, is basically an arrangement invented by a physicist in the 19th century and popularized and by Sir Charles Wheatstone in later. Okay, and then it's called as a Wheatstone bridge. Okay, the Wheatstone bridge basically looks like what you can see from the slide. Okay, it basically has four arms, A, B, C, D. Okay, and each arm has a resistor. Okay, either known or unknown value. Okay, basically it is used to measure an unknown electrical resistance by balancing two legs of a bridge circuit. Okay, and then one leg is include the unknown component. Okay, unknown component. And then this bridge use a sensitive galvanometer. Okay, how basically, okay, it has four arms here, A, B, C, D. Between A and C, there is a fixed resistor R2, CD R1, BD another resistance usually. Okay, let's say this is the unknown RX, unknown value, and another one here AB is the variable uh, resistor which we uh, change the value. And between A and D, we give a voltage supply, okay, DC voltage supply to the Wheatstone bridge. Okay, so and then between B and C, there's a galvanometer. Galvanometer will basically est estimate the condition of the bridge. Okay, when we turn on the circuit, when the bridge is not in balance, meaning that Ig is not equivalent to 0 ampere. Okay, not equivalent to 0 ampere. That is not balanced. Okay. Then when the after that we adjust the resistance here between A and B until we get the condition where Ig is equivalent to 0 ampere or VBC or the voltage potential between VBC equivalent to 0 volt. So that is when the bridge is in at balance. In other words, it is when there is no deflection shown by the galvanometer. Okay, so galvanometer, the purpose is to check whether the bridge has reached balance condition. Okay, and then later we will use that information, that condition to estimate what is the value of Rx. Okay, so how does that work? Okay, okay. Let's say we have this circuit. Okay, R1, Wheatstone bridge, R1, R2, R3, and Rx. Okay, so there are few ways we can prove this final equation. Okay? This final equation. Okay? We can follow the from the value of current. Okay? So we know that this is the power supply. Okay, let's say this is point A. We take this as B, C, O, D. Oh, sorry. Change. Let's redo that again. Okay, let's say we take this as point A. This is as point B. Okay, this is point C, and this is point D. Okay, point D. Okay, so we know that this is a branch. Okay, the I1, I2. Okay, let's say here between A and B, there's a galvanometer. Okay, galvanometer G, and we assume that IG here. I is supposed to be a current here, IG. Okay. So at point C, we know that let's say this is the main current I. Okay, this is the main current. Main current. So I at point C, at point C, we know that I, okay, is equivalent to I1 plus I2. Okay, I2. Okay. At point D, we can write that I1 equivalent to I3 plus Ig. Okay. Point B, we can write uh, I2 equivalent to Ig plus Ix. Okay. But remember one of the bridge on one part or one arm of the bridge. Let's say R2 is a big variable resistor and Rx is unknown value. So we adjust R2 until Ig is zero. Ig is zero. Okay. So when Ig is zero, okay. So when Ig is zero, I1 will be equivalent to I3 and I2 will be equivalent to Ix. Okay. So this is when it's balanced. So when Ig is zero or VAB is equivalent to zero volt. Okay. Okay, so I1 will be equivalent to I3. Okay. So the circuit, okay, will be like this. Okay. R1, R3, R2, Rx. So this is E. Okay. So when it's balanced, so Ig is equivalent to zero or VAB equivalent to 0 volt, the potential. Okay, this is as good as open circuit. Okay, between A and B. So the voltage drop here, okay, R1 across R1 and R2 will be equivalent to the E. Same goes to R2, which in series with Rx. Okay, so we can do KVL here, then we get this relationship. Okay, and then the second we KVL here Kirchhoff voltage, okay, law, then we get this equation. Okay, okay, after we get these two equation, okay, so we know that I1 equivalent to I3 equivalent to E over R1 plus R2. Okay, and then next, okay, we know that I2 equivalent to Ix equivalent to E over R2 plus Rx. Now you have two equation, two equation. Okay, so how do we? So, okay, when you know I1 and I3 and then I2 and Ix, how do you work until you get this equation? Okay, so you just you you can do two, either solve the equation, okay, by using voltage divider, or you can just divide yang look profit here. Okay, now let's start here. Okay, from uh, how we can move from this to this equation. Okay, uh, so okay, I prefer to use the other method that I prefer. Okay, so we have V A B here. Okay, okay. So we draw the circuit A B. Okay, uh, so this is basically VA. This is basically VB. Okay, and R1, R2, R3, and this is Rx. Okay, E. Okay, so we know that, okay, when this Wheatstone bridge is at balance, okay, so here let's say IG, okay, let's say this is IG, is equivalent to 0, okay, or in other words, VA minus B, which equivalent to 0, or VAB equivalent to 0 volt. So remember, VA minus VB equivalent to 0. Okay, there is no uh, deflection on the galvanometer. Okay, or the circuit is in balance. Okay, so VA minus VB equivalent to 0 volt. Okay, that's the first relationship that you need to know. Okay, so VA, okay, we can estimate using a voltage divider. Okay, the voltage divider. So VA equivalent to R3 multiply with E over R1 plus R3, while VB, here VB equivalent to, here is Rx, unknown value, Rx multiply with E over Rx plus R2. So these are the three terms, okay, that very important to use to find Rx. Okay, so we know that VA minus VB equivalent to 0 volt. Okay, therefore, okay, we replace in VA into the first equation and VB into the first equation. So we get R3 over R1 plus R3 multiply with E minus Rx multiply with E over R1 plus R, oh sorry, Rx plus R2 equivalent to 0. Okay, and R3 over R1 plus R2 equivalent to Rx minus E over Rx plus R2. So this cancel. Okay. So we have R3 multiply with Rx plus R2 equivalent to Rx multiply with R1 plus R2. Okay. So yeah, we get R3 Rx plus R3 R2 equivalent to Rx R1 plus Rx R2. Okay. To any other anything that we can cancel. Oh, typo somewhere. Let me check. Rx R3 R3 Rx R2 Rx. So sorry, Rx typo. Yes, yes. Can see. Try to find where R3 Rx R3 R2. Oh yeah, here. Sorry. Oh, let me rewrite that again. Okay. So R3 Okay, okay, so we have R3 multiply, I think this part is okay. Minus, okay, so this is supposed to be R3. This one Rx, R2 equivalent to Rx, R1 plus R2. I hope. Okay, R1, R1 plus R3. R1, oh yes, R1 plus R3. Okay, yes, okay. So R3 Rx plus R3 R2 equivalent to Rx R1 plus Rx R3. Okay, so this one cancel. Okay, so finally Rx will be equivalent to R3 R2 over R1. Okay, so we can go, if we know R3, okay, R3 is 50K, okay, multiply with R2 is 20K, divide K by R1, eh, R2, sorry, R2 is 10K, and R1 is uh, R2, R2, yeah, R2 is 10K and R, okay, R1 is 20K. Okay, you can, we can solve that. 150 multiplied with 10 divided by 2. Is it 15 multiplied with 10 divided by 20? 7.5p. That's supposed to be a thank you for the answer. Okay. Right. Let's see on this one. But you can quickly, if you understand the concept, okay, you can quickly know that R1, okay, divided by R2 will be equivalent to R3 divided by R1. So, but you have to first solve lah, or you have to know how is the equation is derived, okay, before you get, okay. Okay, so this is a Wheatstone bridge. Okay, used to measure the deformation of a pillar of a bridge. Okay, it shows the circuit connection to the strain gauge for measuring the deformation of the pillar. So basically, today we have a bridge. Okay, bridge, and then the bridge. Okay, there are large vehicle moving on the bridge, okay, like lorry, car. Okay. So it create a force, okay, force to and then there's a support, okay, on the bridge. So to measure the deformation of the pillar, okay, the pillar, a strain gauge is used. Strain gauge is basically a sensor, okay. It looks like a handy plus where you paste, okay, paste the sensor on the surface of the pillar. So when the pillar is deformed, either expand or de-expand, so it also deform the surface of the strain gauge. So strain gauge is basically a piece of wire, so small wire. So when the strain gauge is elongated or deformed, it will change the resistance value of the strain gauge. Okay. So in this application, the strain gauge is placed on the pillar, and then the strain gauge, okay, is uh, configure into a Wheatstone bridge. Okay, Wheatstone bridge. Okay, as shown in this figure. Okay. The question is that at night, no cars are on the bridge, therefore there is no reading. So at night, okay, the bridge is at balance. Okay, the bridge is balance. Okay, so when it at balance means that here I this meter Ig will be equivalent to 0 at balance. Okay, balance. Okay, or V M N equivalent to 0 volt. So no voltage potential between M and N, and point M and N. Okay, no potential drop. So Ig is equivalent to 0. Okay, so um, during balance, okay, we know that, okay, quickly we know that it balance RC divide by, let's say, R strain, RS, will be equivalent to RB divide RA. Okay, how do we get? We use the uh, derivation, the balance condition. Okay, as long as you understand, okay, that's fine. Okay, okay, RS divided by RS equivalent to RB divided by RA during the balance. This is balance. Balance means that I equivalent balance. Okay. So quickly, for question 1, we can estimate the value of RS. RS will be equivalent to RC multiply with RA over RB. Okay, which give the answer of 125 ohm. So quickly you can get the answer 125 ohm. Okay. During the day, there are car on the bridge which cause deformation on the pillar. Okay, deformation, and the value of the strain gauge reduce to 0.5 ohm. What is the voltage reading of the meter? Okay, what is the voltage reading of the meter? Okay, but this is quite tricky. Uh, I don't think the answer will be direct. Okay, I think the question is not again. They don't have full information here. Okay, it does not, because we need to know what is the internal resistance of the meter here. Okay, you need to know what is the internal resistance of the meter before you can calculate the value of the voltage meter. Okay, there are one information missing here. Okay, but anyway, okay, when it's not balanced, okay, supply is 6 volt. Okay, and this is right. when it's not balanced, so VMN is not equivalent to zero. Okay, this is let's say the meter. So this is not equivalent to zero, not equivalent to zero. Okay, when not balanced at night, reduce to 0.5. So RS has reduced about 0.5 ohm. So now 125 minus 0.5. Okay, assuming RC is 25 ohm. Okay, 25 ohm. Okay, and here RB is 500. Okay, and RA is 250. Okay, basically to solve this, we need to find the equivalent Thevenin circuit. Okay, and then we need to know what is the uh, what internal resistance of the galvanometer. Okay, internal galvanometer. Okay. So the answer is not that straightforward. Okay. Is there any information about the galvanometer? No, right? Where do we? Hmm, what is the usual value? Okay, let's say lah. Okay, galvano RG meter. Okay, RG. Let's say the meter value is 1 kilo ohm. Let's say 1 kilo ohm. Okay, 1 kilo ohm. Okay, when not balanced, let me. So when it is not balanced, before we can determine the output of the meter, we need to find the equivalent Thevenin, so VTH Thevenin, R Thevenin, what is the Thevenin? Okay. And then this is our meter G. Okay. Plus minus VQ. Okay. So our VG will be RG multiply with VTH divide RG plus RTH, the Thevenin equivalent circuit. So we need to find the Thevenin equivalent circuit seen from point M and N. From point M and N. Okay. First, we need to find what is the equivalent Thevenin. Okay, Thevenin, or what is the equivalent circuit. Okay. So between M and N, what is the MN? Okay. To 6 volt. Okay. So to determine what is the equivalent value, equivalent resistance value, okay, to find Thevenin, what should we do the power supply? We have to short circuit the power supply. Zero. Okay, to find RTH, so we need to short circuit 6 volt. 6 volt, short circuit. Okay, short 6 volt. Okay. So the equivalent circuit seen from point M and N. Okay. We have M. So what is the RTH here? RTH. So here 6 volt, we short. 6 volt, we short this one. Okay. So this is 250 ohm. This is RS 125 minus 0.5. Okay, 124. 124.5 ohm. Here is 500 ohm, and this is 250 ohm. Okay. Then first we need to find what is the equivalent resistance value between M and N. Okay. When you find the equivalent Thevenin value, then we need to find the equivalent Thevenin voltage between N and M. Okay, how to find what is the equivalent Thevenin value between M and N is okay. Okay, put back the power supply. Put back the power supply. 6 volt. And then calculate what is VTH here, seen from here. Okay. So when you know what is the value of the Thevenin value, resistance value, then you know what is the Thevenin voltage value, and we can estimate the value of the voltage value of the meter where using this okay, RG multiplied with VTH over RG plus RTH. Okay, so it's not that straightforward, but because this that is how you solve the question. I'm not going to solve it because basically this is missing information. So this question need to know what is the internal, need to give what is the internal value of RG. Okay, it's not, you cannot calculate when it's not when the bridge is not balanced. You cannot use this relationship. Okay, this is only when the bridge is not balanced. When the bridge is not balanced, you have to go for Thevenin analysis. Okay, Thevenin analysis or Norton circuit analysis. Okay, that is when it's not unbalanced. Okay. Yeah, this is basically when Thevenin, you have to for the Thevenin equivalent value, and also the now we just now we discussed about the Wheatstone bridge. Now we discuss about the Kelvin bridge. Okay, Kelvin bridge is basically a modified Wheatstone bridge. Okay, it is used to measure low resistance value. Okay, low resistance value. Okay, range between 0.01 to 25 ohm. Okay, so basically, it looks like a regular Wheatstone bridge. Okay, a regular Wheatstone bridge. It has a sorry. So basically, it has okay power supply. Okay, it has a okay, R1, R2, and galvanometer in the middle. Okay, and Rx, R3, X is the unknown value. Then it has some modification. There is a thick wire, okay, connected like I show here. Okay, this is a thick wire, okay, creating a an extra connection. Okay, extra connection. Okay, and in the end, this extra equation will show the answer. The answer. Okay, this relationship. Okay, Rx equivalent to R1 over R3. Okay, okay. How this is the one of the way the equation is derived. So I want to show you the my method. Okay, my method how we find this. Okay, uh, find this equation. Okay, so let's start by redraw the Kelvin bridge. So this Kelvin bridge, this between this x, k, y, z will okay, between that point we will introduce uh, a significant resistance value lah. I will show you. X, y, z. This is X. This is R3, R2, and R1. That's the galvanometer. Okay. So there's an introduction of the thick wire between point X and Z here. So it will introduce a significant resistance between XY, YZ, and XZ. Okay, so basically it will look like this now. Okay, RX. Okay. Point X, point Y, point Z. Okay. So here, see this is RCB. Okay. This is RY and this is RAB. Okay. This is R3, this is R1, and this is R2. Okay, so to this thick wire, it introduces a resistance between X and Y is called RCB, between Y and Z called RAB, and between X and Z point, okay, called as RY. Okay, galvanometer. And it is known that the resistance RCB over RAB, the ratio of RCB over RAB is equivalent to R1 over R2. So this is first one. Okay. Okay, and then RAB plus RCB equivalent to RY. So this is the ops second uh, relationship. Okay, RAB plus RCB equivalent to RY. Okay, so next we need to transform the x y z, x y z. So basically, if you look here, x y z, x y z. So here is RCB, here is RY, here is RAB. Okay, so it's basically looks like a delta connection. Okay, between point X, Y, and Z. So we transform transform that into R1, R2, and R. This is R1 prime. This is R2 prime, and this is R3 prime. Whereas R1 prime equivalent to RCB multiply with RY divide by RAB plus RCB plus RY. Okay, and from this two, okay, RAB plus RCB is equivalent to RY, so we can write RCB multiply with RY divide by 2 RY. This is R1 prime. Okay, and, conversion between delta to star. Okay. Okay, so next we have R2 prime equivalent to RCB multiply with RAB divide RA plus RCB plus RY. Okay. And we can write that as RCB multiply with RAB over 2RY. R3 prime will be equivalent to RAB multiply with RY over RAB plus, this is AB, RCB plus RY equivalent to RAB multiply with RI over 2RY. So R3 equivalent to RAB divided by 2. Okay, so we get R1 prime, R2 prime, and R3 prime. So we convert, okay, from delta to star. So this Kelvin bridge, okay, now let's convert this part. Hang on. Okay. Okay, so we have this Rx, this point X. So this is our R1 prime. Okay. And this is point Y. So this is our R2 prime. This is Z point. So this is our R3 prime, and this is our R3. So now it looks like a regular Wheatstone bridge. You remember that this is IG, okay, okay, equivalent to 0, okay, IG here. So this point here in the middle, it will be as good as the open circuit. Okay, open circuit. Okay. So this is a Wheatstone bridge. Okay, this is a Wheatstone bridge. So when we can consider at this point, this is as a balance. Okay, let me. Okay, so at balance, okay, this part, well, we know that at balance, we know that R3 plus R3 prime divide by Rx plus R1 prime equivalent to R2 R2 over R1. Right. Okay. So at balance, okay, this on the bottom left, okay, R3 plus R3 prime divide by Rx plus R1 prime will be equivalent to R2 over R1. Okay. So we rearrange, okay, we rearrange this, we get that Rx will be equivalent to R1 over R2 multiply with R3 plus R3 prime minus R1 prime. Okay. Okay, next we know that R1 plus R2 multiply with R3 prime. So R3 prime here is RAB over R2. Okay. And R1 prime is RCB over 2, right? Okay. From here, R1 prime is RCB over 2. Okay. Okay, so can go on here. So we get R1 R3 over R2 plus R1 RAB over 2R2 minus R CB over 2. Okay. Now look at here. We know that R1 over R2 is equivalent to RCB over RAB. So R1 R2 over R3 plus, here we know the RCB, R1 over R2 is equivalent to RCB over RB. So here RCB over RAB, okay, 2 multiplied by RAB minus RCB over 2. Okay, so here cancel. Okay, so this is plus RCB over 2 minus RCB over 2. Okay, so finally we get here Rx. Okay, and here go back here. Finally we get Rx equivalent to R1 multiply with R2 over multiply with R3 over R2. Okay. So that is basically how Kelvin bridge is derived. Okay, the relationship. Okay, this is the other way we can follow. Okay, this question based on figure 1. Okay, let me. Okay, so based on this, what's the ratio of RA? If the ratio of RA to RB is 1.K, okay, 1.2K, okay, and on. So if RA over RB is 1.2K ohm, okay, R1 is 10 ohm and R1 is 0.5. What is the value of Rx? What is the value of Rx? So we know that Rx over R2 equivalent to R3 over R1, isn't it? So R3 is not given. And another relationship, ratio RA to RB is more. R3 is, oh, okay. R3 is 10K, 1K. So direct lah. I think you can find Rx value is R3 is 1K, okay, divide by R2 over R1. and from here R2 over R1 is equivalent to 1 over 0.5. So that's equivalent to 2, isn't it? From that, I think the answer is 2K. Okay. At balance condition, calculate the current flow in R3. So if you want to find the balance condition, okay, balance condition, the value of R3, okay, first, okay, the hint is to convert this, okay, delta, okay, to star. Okay. How the ratio RA over RB, and then there's another equation which RA plus RB is equivalent to RK. Okay, that is another equation. Okay, you can find so the next hint is to find the value of R conversion from delta to star. Okay, I think I stop our class here, and then we continue next Thursday, and then we discuss, come back to this question lah. Okay. So with that, I conclude my class for today. For now, don't forget our test one, 2nd December until chapter 2B. Okay, and then I think by next week, or by next week we should have covered all the topics in 2B. Okay, with that I conclude our class today. We meet again on this Thursday. Okay, thank you. Assalamualaikum.